Okay. Uh, in this class, we mainly will be focusing on the lexicon analysis part, uh, and also we'll be looking through some fundamentals that is required to understand all the phases of compiler design. Uh, but some portions of finite state machines and regular expressions will be requiring while understanding the syntax analysis or later phases. So I will try to introduce those things in brief so that it may helps you to understand those segments. Now let's concentrate on the lexicon analysis phase. Okay, just wait a minute. I am sharing my screen here. Okay, I hope you can see my screen. This is the document already I have shared with you all. Uh, uh, Mainly the compiler design, the paper compiler design, it is closely related to the computer science people. Basically, what happens that when you write some codes in any platform, whether it is a C or C++ or Java, then definitely a compiler exists. That compiler process that code and checks whether the errors are there in the codes or not, and then it gives the output to the screen. After that, you execute the codes. So the main point is that the compiler does that error finding part. So correction of errors, whether it is done by compiler or not, that is the thing that we will see later. But the point is checking of errors are done by compiler. One point is very clear. Second point is in terms of optimization. Let you are writing a normal programming code, let for a bubble sort. It has a complexity of order of n square, for example. Now, this complexity is very static complexity. That means the code that you have, if you change the code, then sometimes you may reduce the complexity using some continuous statement. You can reduce the complexity from order of n squared to order of n. That is different. But my point is order of n squared, generically it is order of n squared. Now you cannot reduce the complexity beyond that order of n squared in generic sense. But if a bubble sort is there, whatever the registered allocations or whatever the memory space are required to execute the code, whether in terms of that, whether the optimization is possible or not, which I wanted to mean that in machine level optimization, when the machine level code is generated, machine level code means microprocessor level code, that you understand the syntax, printf, scanning, but the compiler, after that machine level code is being generated, it generates some, now that LDA command, move command, MVI command, that type of commands are there. Before generation of that command, some intermediate code is being prepared, then it is forwarded to the microprocessor. So before the microprocessor level code is being generated, whether any sort of optimization can be performed or not. So compiler design has these two phases, means two tasks. That first is finding errors, and the second task is perform optimization in terms of level of complexity or in terms of space optimization. Okay. So let's see what are the different stages of compiler it has. Basically, I hope you can see in my screen. Let me zoom out. Basically, when I have a source program, you can see when I have a source program, let me check to read. When you have a source program means you have written a small C code that I can categorize as a source program. It passes through this number of phases: lexicon analyzer, sometimes it is called a scanner; syntax analyzer, it is called as parser; then semantic analyzer, intermediate code of generator, code optimizer, and then This is code generator means final code generator. Okay. Now, if I consider the first part, when you are feeding a normal C code through the lexicon analyzer, basically these first three phases, this phase, and this phase, lexical, syntax, and semantics, this deals with finding of error, finding errors in codes. And these last three phases, intermediate code generators, you can check that once the error findings are completed, then intermediate code is being generated, then it is optimized, then the machine level code is generated. So in these three phases, I can tell or I can say that it performs the optimization. Okay. So that number of register allocation before the microprocessor level register allocation, it is reduced. Finding error, the first task, first three phases deals with, the last three phases are for optimization. Okay. And you one very symmetry you can find all the phases are being connected with a special square box like architecture that is called as a symbol table. What is symbol table and what are the different phases and what I have written here, the token generated, syntax tree form. I will be discussing all those things one by one later. Now, one thing you have to understand here, just you may not remember, no need to remember, just listen the sentences. When you have a C code you have written, when it passed through the first phase lexicon analyzer or the scanner, it generates the tokens. So the terms maybe you may not be familiar with these terms, what is called token. So we will introduce those terms later. Then it passes through another analyzer that is called syntax analyzer. That means the tokens are feeding through the syntax analyzer, correct? C code is fed through the lexicon analyzer. Tokens are generated. Tokens are fed through the syntax analyzer. Then syntax tree is generated. Syntax tree is fed through the semantical analyzer. Then annotated parts tree is being formed. So what is annotated parts tree? We will also look into it. So in these three phases, if I consider 5 plus, let it is 3 plus 2 minus 1. So if I can categorize, this is a C code, and C code means the expression it needs to evaluate. So 3 plus 2, that means 5 minus 1, that means 4. What it does in the lexicon analysis phase, if this code is being fed through the lexicon analyzer, it categorizes this is a token, this is a token, this is a third token, fourth token, and this is a fifth token. So in the first phase, it generates the 5 tokens. In the syntax analyzer phase, it forms a syntax tree, correct? Syntax tree means, in automata theory paper, when you represent some expression in form of tree, that is called a syntax tree. You have heard about the binary tree, which has two child, left child and right child, but the syntax tree has a different architecture. This is a 3, this is 2. I cannot write 2 here. This is a minus operation I am performing. Here 2, then 1. So 3 plus 2 minus 1. Here you can see that this is a tree. If I evaluate the tree, then definitely the results would be 4. Whatever sense I have expressed the tree, that is a different, because the tree may have different architecture in terms of expression. Why I am telling, because you can put minus here, you can put plus here, then you can put 3 here, you can put 2 here, you can put minus here. So that is one more option. This tree is possible and this tree is also possible. 3 plus 2 minus 1, 3 plus 2 minus 1. Now, as I was telling, in the token generation phase, these 5 tokens are generated. In syntax tree phase, corresponding to this expression, a syntax tree is being developed. This is a syntax tree, either in form of this tree or in form of this tree. Correct. This is called syntax tree. Now, what is called annotated parts tree? Now, once the tokens means the symbol, the digits, the variables are extracted here. So these are tokens. I have formed a tree. Now, what is the expression? What is the final value of this expression? Initially, we checked it is the value is 4. But who said the value is 4? Basically, from token tree is designed. From this tree, the value evaluation of the root node is being done in this semantical analysis phase. That is called annotated parts tree. That means the same tree you have, I am taking the first tree that I designed, that it was minus, it was 2 and this is 1. So here the evaluation is down from bottom up. 2 minus 1 means it is 1. Now 3 plus 1, that means it is 4. Now the root node value, you know, this is a root node, this is a child node, these are the 3 leaf nodes. Now the value is 4. That means the value 4 I have obtained here. This value, how I have find it out? By evaluating the parts tree. Now this tree, once the values of internal nodes are being evaluated, this internal node has a value of 1. This internal node or final root node value has a value of 4. So this tree will be categorized as annotated parts tree. I hope the idea is clear. That if I assume this is a C code, first tokens are separated, then syntax tree is being formed, that means in form of a tree. Then evaluation of internal node values or the root, and finally the root node values is being done, and that is called annotated parts tree. Regarding this intermediate code generator and code optimizer and final code generator, we will talk later, because this intermediate code generator means it will generate the machine level codes, correct? And how the optimization is being done. So some optimization, because here once this tree is being generated in this phase, in intermediate code generator part, some 3 address, 2 address or 1 address code is being formed. So what are the different codes are actually there, we will be looking at later. Once those codes are being generated, correct, then a code optimizer, some rules are there in code optimization, like dead code elimination, loop variable elimination. uh, so some more techniques are employed here in optimization process, so that the extraneous elements can be removed. Or let I have a declared a variable in a code, I never have used that variable. How that variable is being actually checked by a compiler, that whether this particular variable is never ever has used in a code but still is being defined. You know that when a variable is being declared in C, immediately for that variable a memory space is being allocated. If you declare such 1,000 variables but not using them, definitely it will consume a memory space. So compiler cannot allow this process. So finding that dead part in a code segment, how it is being done, that is part of code optimizer. We will be looking at that part later when we will be entering that portions. Once the dead code are being eliminated, then the final code, that is microprocessor level code, which can support the microprocessor. After this level, there are no opportunities are there to reduce or to minimize the complexity in terms of space or in terms of time over the codes. Okay, so in the first 3 phase, generation of token, formation of a tree, third phase, evaluation of a tree, intermediate code phase, intermediate code in 1 address, 2 address or 3 address format. In code optimization, like dead code elimination, loop variable elimination, reduce strength reduction, different techniques are there. In code generator part, we generate the final machine level code which can accept by the microprocessor. Okay, basically these are the phases are there in the compiler, and we have to look through all the phases one by one. One thing you can, as I have said previously, that the symbol table is being connected with all the phases in this architecture. We will be looking in the symbol table architecture later, but one thing you can be sure with that, symbol table like a head of your body. That means whatever the sense you get from all the organs from your human body actually is being sensitized or being controlled by your brain. So symbol table is architecture, or we should say that it is a data structure for every verification. When lexical analyzer verify that let x equal to 3 plus 2 minus 1 if I had taken. So whether this x is really a variable being taken or declared by the C or not, For that, it checks the symbol table. So symbol table is acting as a data storage area which stores all the information of all the related things. I hope that this, whatever the sentences I am pronouncing, this might not be clear here about the symbol table. Later we will be looking into it, but as of now you can take it in that way, that symbol table is a data structure which which is being connected to all the phases of compiler. For verification of any data, each phase contacts symbol table and get the verified result from the table. Okay, perfect. Now, uh, before I am entering into the each phase separately lexical syntax, I am going back and I am showing a small portion. I hope this will be very convincing for you. So when compiler design phases comes, so we have shown the different stages of compiler, but when compiler design process requires, basically when you write a source program, I have written a source code abc.c, this is a file name, and I have written a code like has defined x5, this is the main function, open brace, int y equal to 5, and I have given y equal to x, not 5, because I want to initialize uh, 5 into y already, though y is 5, but still I want to initialize 5 into y, this 5. And this is a code close brace. It will be better if you take it y as a 4, then it will be good for you to understand. Now, once you write the code, it first passes through the preprocessor. In the preprocessor, it generates the pure high-level language. So the code had an extension abc.c. Here it changes to abc.i. Correct. What happens when you write a code abc.c and passes through the pre-processing technique? Then this has defined part is being removed. Correct. In has defined part, what happens? X equal to 5, correct, you have taken. So this line is being erased. And for y, the value of x, this line means this has defined part, not the entire segment. It takes the x value as 5. So y, it assigned the value of x, it is a 5. Correct. In the pre-processing part, mainly the has defined part are being removed and the exact value allocation. So x was there, so that means 5 is being allocated to y. Though initially I said y equal to 4, now the value is overwritten with the new value, it is 5. Then it passes to the next phase, it is a compiler. So this file, whatever after removing the has defined clause, it passes to the pure high level language part. Here it enters through the compiler, and you know all the 6 phases are there in the compiler. The first 3 phases are deals with the error finding part, and last 3 phases are dealing with the code optimization part. Once that part is done, you can remember in the last phase of the compiler, in this phase, I said it generates the microprocessor level code, which can accept the microprocessor. So here, basically, before generating the machine level code or microprocessor level code, another in-between stage is there, that is called assembler. So here from compiler, it generates the assembly level code. So the extension is changing to abc.i to abc.s. This is the real-time extension, whatever I'm showing here. Then once it's processed through the assembler, then the final machine level code is being generated. Basically, from the 6th stage, I said this generates the microprocessor level code. Mostly it is being done, but sometimes it passes through the assembler for cross verification and fine tuning of the machine level code. And in the machine level code, again, you check that from abc.s to another object level code is been generated, that is abc.o. Then linker and loaders. Linker and loader means in your code, you may have called several function calling you have used. Correct. You have used some different header files. So how to connect those header files located in different directory? How to connect with different system calls pertaining to different libraries or your own defined system calls that is being done in the loader linker part, and then the executable file you see in terms of exe is being generated. So this is the pathway from abc.c to abc.i to abc.s to abc.o to abc.exe. Correct? But this is the route I have shown, but you have to focus on the compiler design phases, all 6 phases. You will be looking on onto that aspect on. Okay. Now, before I introduce the lexicon analysis part, so we have to go through some fundamental portions, and here we are going to introduce that portion as well. First portion is few terms, actually not portions I should say, that mm, first term is token. What is token? Please go through the sentences that I have used. It includes keyword. Let I have written int a5 semicolon. It contains keyword. It contains operators. It contains identifier. Identifier means any variable. Operator means, asterisk, ampersand, division sign, all are operators. Keyword means that how many keywords are there in a certain language. It depends on language to language how many keywords are there. After that, the constants are there. Uh, Constant are there. Then function symbols are there. Punctuation symbols are there. Like semicolon, double quotes, these are there. Now here, if I consider in a5, that means this is a keyword. I can consider this is the first token. It is identifier, is a second token. 5, this is a constant, this is third token. This is a semicolon. Semicolon, it comes under the punctuation symbol. This is the fourth token. So for this instruction set or the code that I have written, it has contains 4 tokens. So what is token? Mainly whatever you write in normal sense, what is separated by space, that is categorized as a token. But some exceptions you have to remember, we will be looking into it. For example, in this code, uh, int x equal to 5, here 5 tokens are there. Same way for equal to, this is an operator. So this is an assignment operator. 5 is assigned to x. So first 1 token, this is a second token, this is a third token, this is the fourth token, and this is the fifth token. Correct? Now, one exception you have to remember, in most of the questions it is being asked, whatever is being declared within the double quote, that is taken as a single token. Correct? If I write in this way, I am here within the double quote, then it is categorized as a single token, double token, third token. But if I write in this double quote, then it will be categorized as a single token. Now, for this code, example number 3, printf, I am here. How many tokens are there? This is 1 token. This open bracket single token, second token, from this double quote to here. This is third token. This is the fourth token, and this is the fifth token. So all 5 tokens are here. So total number of tokens are 5. Correct? Okay. I hope the idea is clear. What is token and what is identifier? Identifier means variable names, or even it can be a function names. Here I have written what is identifier. It can be a variable name like x or y or temp. It can be a array name, like when we declare an array, this is an array, this is array variable name, this is an array variable name. Or even the function call, when we call a function add or sub, our own defined function, that function name is also comes under the identifier. Okay. The next term, parts tree, though I have introduced the term parts tree here, that form an expression. When it is expressed in form of a tree, that is called a parts tree. The same things again I am going to repeat here. It will give you more clear idea, some more points I'm going to add here. Let 9 minus 5 plus 2, this is the expression, this is the expression I have to evaluate. So when 9 minus 5 plus 2, when I have to evaluate, this expression is cannot be very static expression, because compiler, when you feeding this 9 minus 5 plus 2, definitely it can evaluate 9 minus 5 equal to 4. 4 plus 2, that means 6. That is true. But if you feed a different expression, definitely it should compute this value accordingly. But definitely it should govern by some grammar. Grammar means a grammar Vn, sigma, P and S. This is called a grammar different part. So Vn set of non-terminal, set of terminal, production rule and start symbol. So what is called grammar? Let when you are formulating some sentences, let when I am pronouncing some sentences, it is based on some grammar. If I make any uh, mistakes information on my sentence, and if I am exactly following the grammar, that means the grammar is incorrect. But it is not possible. In my sentence, if I am pronouncing, again I am repeating, if I am pronouncing the sentence as per the grammar principle, exactly following by the grammar principles, but I find out, but someone find out that my sentences are incorrect, that means the grammar that is being defined, that is incorrect. Okay. So that is called grammar. That means grammar is very generic component. From that grammar, the strings are there. So my string 1, string 2. So my sentences are categorized, can be categorized as different strings. That comes under a grammar. VN means, I hope you should see one video on what is called grammar in automata theory, that will give you more clear idea. VN means set of non-terminals. Non-terminal means if I express this, this is called the production rule. Production rule means from where I can expand the entire tree, or how I can generate the entire tree based on which rules that are called production rules. This can be categorized as P. So S means start symbol. For this, whatever the tree I have produced, or if I consider this is a production rule, for this, the S is list. S is the variable list, because I have the one variable list from where I have started the root node. So the root node is considered as S. Sigma. Sigma means set of terminals. What are the set of terminal? Terminal means which terminates. So here the values, you can see that the digit, the component is here. The digit, if I consider this expression, list is generating list plus list, or list minus list, or digit. So what is called sigma? Here the sigma actually contains only the variable digit, because the only terminal that exists. What is Vn? Here, what is Vn? If I write non-terminal, so I can expand only one non-terminal exists, because here it is list, because non-terminal means which I can expand. This is the list, this is another variable. If let, for example, instead of this list, it was x plus y, and x is expanded to list 1 to list 2. So definitely this x and y will be coming under the set of non-terminal. So here only the one variable exists, that is. So non-terminal means variables which I can expand. Again, I'm repeating that if this list was generating the variable x and y, and x was expanding to list 1 and list 2, for example, then under the non-terminal category, x and y would have come also list 1 and list 2. So list 1, list 2, x and y would have come under the category of set of non-terminals. I hope you have understood the part. Okay. Now, as I was telling that this is a grammar. For example, it has a set of non-terminal. Here I have it declared. It is a list. Terminal, sigma, let's digit. P for production rule. These are the rules. These are very important. Production rules, because based on the production rules, the grammar is being checked. and S starts for start symbol, the root node here, the list. Now, if I have to realize the value 9 minus 5 plus 2, the thing is that I have to use a grammar. 9 minus 5 plus 2, you can assume this 9 minus 5 plus 2 with a string, means my sentence. Let I am forming a sentence, I am teaching the compiler design paper. So this is a sentence and you can assume 9 minus 5 plus 2 is equivalent with that sentence. Now, the sentence I have formed based on a grammar. Let the grammar, the sentence I have formed, I have formed a sentence S1. I am teaching the compiler design paper. And this sentence is based on a grammar T. Correct? In the same way, this is connected with T. In the same way, if I consider 9 minus 5 plus 2, this value to be evaluated as 6, then before that, this expression needs to be connected with some grammar so that the value of this expression can be computed to 6. So 9 minus 5 plus 2, this is associated with this grammar G, and this grammar has this set of production rules. Correct? That means as I have formed my sentence T using the grammar S1, in the same way, the 9 minus 5 plus 2, this expression to be formulated using the grammar G. I hope the ideology is very clear. Okay. Mean what we have to do? 9 minus 5 plus 2, this string to be expressed using the grammar G, which has this sort of production rules, non-terminal, start symbol, and terminals. So how I am expanding, you see that in the first, I am taking the first expansion, list equal to list plus list, the first expansion I am taking. So list equal to list plus list, the first expansion I have taken here. List equal to list plus list. This is OR symbol. List can extend to list plus list, or list can generate list minus list, or even it can generate digit. So then again this list I am expanding to this list minus list. Second expansion I am using. Finally, list can generate digit. So list is generated digit here. List is generating digit here. And this list is generating digit here. Right? Now I am putting the value corresponding to digit for 9, digit for 5, digit for 2. These values I am putting here. The final value. Correct? So 9 minus 5 plus 2. This is being expressed in fixed operation in terms of 9 minus 5 plus 2. It is expressed. That means if someone has given 9 minus 5 plus 2 plus 3 minus something, that also can be expressed from this production rule, but the tree that I have formulated, that would have been different. So you have to design the tree in such a way that this string can be accepted. The same way, the sentence I have formulated, I am teaching the compiler design paper. I have formulated the sentence in such a way that it should follow the grammar T, the English language grammar that I have learned in my school time. Right? So what we have learned from this example number 4, that a grammar has these 4 tuples, 1, 2, 3, 4. Whatever the strings are being generated, that should follow a certain grammar if it is being specified that those strings are following the grammar. Like my sentence, it's following a grammar T. Grammar production rules are the main part of the grammar. In all the phases of compiler design, mostly we'll be writing the production rules, not the entire grammar. Production rule means the rules from which I can design the tree. This is the foundation stone to generate a part tree, basically, which is the fact. So production rules forms a tree. Expression is being given. From that expression, we have to form the tree. We have to form the tree in such a way that that expression can be realized using the tree, right? I hope the idea is clear here. We have learned about what is called grammar, what are the different tuples, how the string can be realized in forms of a tree that is called syntax tree, what are called non-terminal, terminal, and start symbol also we have seen. Okay. Now, one more portions we have to check here, that though that is not directly related to your paper, but still you have to go through this segment. If how to evaluate, you see that when I am telling that 9 minus 5 plus 2, I am showing 9 minus 5 plus 2 in this way. Why I am showing, I said this is infix operation. So you know that how the in order or infix, pre-order or prefix or post-order or postfix can be evaluated in compiler design, in actually data structure paper already you have shown, you already have learned. Now I am showing a small technique to understand how to realize those three segments, because when in compiler, in lexicon analyzer generates the tokens, syntax analyzer design the tree, but in semantic analyzer, which evaluates the value of the tree, that cannot take the infix operator based expression, mainly changes from infix to postfix, then it evaluates the value. That means here I have shown now that the trees in lexicon analyzer, these are the token, in syntax tree, these are the tree. In semantics analyzer here, this tree directly is not being evaluated, though I have shown here in top-down manner. That is not the real-time scenario. The tree to be converted into the postfix based tree, then some semantical rules will be applied and then will be evaluated. Okay. Now, why I am telling these things? Because you have to know that how the infix, postfix, and prefix can be evaluated in a very simple way. So here you see that if this is the expression is being given, 9 minus 5 plus 2, I don't know what is the expression. If you drop it, if you design a plane over here, and if you drop the nodes perpendicularly, this node dropping the nodes 5, this 2, so what is the expression? This is 9, this is minus, this is 5, this is plus, this is 2. Whatever the expression you will be getting, that will be called infix. If you drop the nodes perpendicularly over a plane, that will be called infix. What is called prefix? For this tree, if I start traversing the tree in this way and start writing plus, minus, 9, 5, then 2, you can see this is the prefix, plus, minus, 9, 5, and 2. What is the postfix? We have to start from the right portion, but in Arabic order we have to write. From the right side we will be writing. So plus 2. So that means plus 2. Then next is minus, then 5, 9, then 5, then 9. So this will be the postfix. That means here this is a postfix operation given, this is the postfix. Okay. I hope the idea is clear. Infix means dropping the node perpendicularly. Prefix means traversing the tree from left to right. And postfix means scanning the tree from right to left, but in Arabic order. Okay, and one more example is being given. You can check out this example by your own to get a more clear view on that. Okay. Now I am coming to the next portion that is called symbol table. Again, I am telling that I have not entered the lexicon analysis phase. Just I am introducing few terms. What are the terms we have introduced till so far? I have talked about tokens. I have talked about identifier. I have talked about what is called grammar and associated tuples. I have talked about the different infix, prefix, and postfix operation. And now I'm coming to the another architecture that is called symbol table. This symbol table, this is called an architecture or data structure mainly. It contains different information. This symbol table will be having thousands of columns. Here, though I have shown some 5 columns, but still it may have numerous columns. Let for the first column is name of the identifier. understanding over the symbol table will be more clear when you will be approaching one lexical phase to the scope. Okay, the net connection is getting problem. Okay, now it's fine. The scope, then the size definitely, and the storage allocation. Some more columns are there. Size means if it is a long int or short int, or whether it is a um, character variable. Depending on that, the size is being required. Storage allocation. What is the memory location? You see that the name of the identifier, putting the this temp, let I have declared this temp as a variable in temp, for example, semicolon. So what it understands that temp is a variable, directly it enters the temp into this table in the lexical phase. Temp enters. Now, what is the type of temp? So this type part cannot be specified in the lexical part, because lexical part has only capability to generate the tokens, not a different, what are the type, what is the scope. Scope means local scope or global scope. So this temp variable, whether the scope is local or global, this can be commented in the semantical phase. Or the size, what, how many memory allocation is required. It can be specified only in the code generation phase, and also the storage allocation, memory allocation. So some is connected with lexical, some is connected with semantics, some field is connected with code generation. Though I have, as I have said, though I have given some 5 columns here, but it may have some numerous columns, thousands of columns. So symbol table is an architecture. When the type of the temp variable is being tried to define, then in semantical phase, then it first checks whether the temp is really exist in the table or not. Correct. So that means in the first phase, temp inserted in the symbol table by lexical analyzer, but semantics perform the cross verification whether temp exists or not, then it puts that is associated type. Or even in the code generation phase, it checks whether the temp is being used by some other variables or not, or in the throughout the code, then only the memory is being allocated. Otherwise, it will be dropped. So symbol table is a structure where all the tokens are being stored in the first phase. Then the different attributes of the tokens. I cannot specify all the attributes of the token in the lexical. Some attributes are coming in the semantics. Some attributes are coming in the code generation part. Not only coming, attributes are coming and cross verification is being done, whether really that variable exists or not, whether it is really long int or short int, like that. So symbol table is a data structure. That's why it should be connected with all 6 stages of compilation, so that data retrieval and cross verification can be done in a smooth manner. Okay, so symbol table is done. Okay, now some more short parameters here I will be introducing here. You can go through it. Like I have said previously, that what is called grammar. One more example on grammar I have given, as some of you have said that some portions on grammar, if I can include in my lecture, then that will be good. So for example, this is a grammar. Vn, sigma, p and s, these are the 4 tuples are there, and here the production rules are there, s to ab, s to asb. Correct, these 2 production rules are given. Now these 2 production rules are given, correct, these 2. Sigma is a and b, means terminals. Vn means this is a start symbol. P means production rule. S means start symbol. Now S to AB, S to ASB. So here you can see that I started with ASB. That means if I design a tree, A to small a, capital S. Here I have given in a sentential format, not in a tree format, to make it a compact. Now, as S is a variable, I can again expand this A in ASB format. A, capital S, and B. Small a, small b are terminal. Again, S can be expanded at A, S, and B. In this way, it can go on. So A, B, B, B. So what you can generalize, in left part, it will be coming A to the power n. In the right part, it will be coming B to the power n. That means same number of A's and same number of B's will be coming in the left part and as well as in right part. And this S variable, how I can express, S can be expanded to AB as also. No? So S can be expanded to A and B also. So that means A to the power n plus 1, if it has, it also will be having n B to the power n plus 1. So that means what is the expression? It is, this grammar is generating what expression? So A to the power n and B to the power n, this is the expression is being generated. So this is the language. This is the language being accepted or being generated by this grammar. What does it mean? It means if you A to the power n, B to the power n means if I take AB, if I take AABB, or if I take triple A, triple B. So whatever the component I can derive from this generic expression, definitely that will be accepted by this grammar. If I summarize, this is a grammar and production rules are given. I try to form a tree and also try to generalize what trees it is generating. So it is generating a tree based on A to the power n and B to the power n format. So that part I have given here. And what are the different sentences? This is a language. These are the different sentences. These different sentences are following this language, and this language is following this grammar. This is the sentences, you can tell in a naive sense. This is following this language, and this language is following this grammar. That means whatever the sentences I am telling, this is on English language. It may be French or German. This English language is following these grammar rules. Correct? Okay. Now, some more small fragment on finite state machine architectures I am showing here. It will make you more compact while understanding the different phases later. For a grammar, so one thing you see, what I have given here, this was a grammar. From the grammar, we have derived a language. From the language, we have checked the different sentences, S1, NS2, and S3 like that. This is the summary of the part in example number 6. Right. Now this S1, NS2, and S3, these are the different sentences. One more option is possible, that these sentences can be expressed through some machine. That machine is called finite state machine. Sometimes it may not be finite state machine. It may be a Turing machine or push down automata. So grammar generates language. Language generates sentences or small strings that are accepted by the finite state machine. That means these finite state machines are designed based on the grammars and also based on the language. So this is a cyclic path. Grammar to language, language to different sentences, sentences to finite state machine. That means whatever the sentence I take, let S100 I taken, that should be accepted by finite state machine. For example, I am starting with the language part. If I am taking a language A to the power n, what is A to the power n? What are the different sentences it can generate? A to the power n, if n is equal to 0, it can generate epsilon. Epsilon means anything, nothing. If n equal to 1, it is only A. N equal to 2, double A. N equal to 3, it is triple A. So that means there is a grammar. From that grammar, this language was derived. From this language, these are the different templates can be designed from the language. Now, what will be its equivalent finite state machine? That is the question. Which can be, I can tell it is directly related to the grammar. So it architecture like it should be, this is the start part. These are the states actually called. This is a Q0 state. If I am giving it is A, So that means it can rotate over A any number of times. But if I am putting a double encirclement, that is called final state. If it is, if I have this state followed by this state, here I am accepting A, here I am accepted B, over A I am moving, that this is a Q0 state, it is a Q1 state. So you check that from here I am starting, from Q0 state I am moving over A, that means it is expressing A to the power n, any number of times they can move. Then it travels through this B path, B, then it reaches to the end part. So that means it accepts a language A to the power n and B. Very simple. A to the power n B means if I take AB, whether it can accept or not, yes, one time A, then B. If I take A square B, double time A, single time B. If I take A cube B, triple time A, then B. It is also fine. In the same way, A to the power n means any number of times A should iterate. So here, why I have taken it is initial and final, because I have to consider epsilon. Because once the token is being taken and being reached here without moving anything over A, after inserting the system, entering the system, it reaches to the final state. That means it is accepting epsilon. Or even it can take any number of A move. 1A, it can be accepted, that's why single A. Double A, it can reach double A or triple A. I hope the idea is clear. So a grammar was given. From that grammar, a language was derived. From that language, this was an expression that I have taken, that sample strings. For that string, what should be its finite state machine? So this would be the finite state machine corresponding to the string that we have seen. And here we have checked that what are the different expression I can formulate if different architectures of finite state machine is being given, right? Now, if I take one more example, if a language is given A, B, so what will be its finite state machine? A means it starts from here, no iteration, it passes to here A, it passes to here B, and it is a final state. You can check double encirclement, final state. If it tells BA, so it is first B, then A, then final state. If it tells A plus B means either A or B. So if it is an initial state, then from Q0 it can reaches to here either by A or can here reaches here by B. So A plus B. If it says A plus B star, A plus B means any number of A. It can be A, it can be B, or combination of A, B, or can be anything. It may not be A, B. So epsilon it contains. A means it can A, only B means only B, or AB, any combination of AB. It can be AB, it can be BA, it can be AB, BA, anything it can be. So the architecture will be, it is inserting here any number of A, any number of B, and it is a final state. Okay. Now if someone tells AB whole star, if it gives you AB whole star, that means every time it will follow the pattern AB. AB definitely will be there in the pattern. This is a B. AB like that. So it is a start part. Here I am following A. Here I am following B. So this path is generating AB, and this entire path is giving an iteration over AB. Why? Because you check that when I am giving an iteration over here, X, so it was generating X star. Here I am expressing X as AB. So that means X star, if I am having an X expressed as AB, definitely AB star. That is very simple. You need to formulate in that way. Okay. If someone tells A to the power M, B to the power M, it is a language. A to the power M means it starts from here. It accepts what are the languages? A to the power M, B to the power M. If it is a language, what are the sentences it can accept? M can be 0. So then B can be 1. B also can be 0. A can be 0, B can be 0. So that means it can accept epsilon. If B is 0, A is M1, means M is 1. That means it will be A. If M is 0, B is 1, then it can accept B. So, or even any combination, it can be AB, it can be, it cannot be BA, you see, because BA, why not possible? Because you see B is coming later part. So this sentence, while forming the different sentences of the sample strings, BA is not possible. But in earlier case, when we had taken that part, AB, BA, A plus B star, this was quite different. Because any combination with A and B, it was different. Architecture was different because it can move over A, it can move over B. Anything, anytime it can move. But when this path is unidirectional path I am generating, A to the power n, B to the power n. So here, it is moving over here. A to the power m means any number of times it can iterate. Then epsilon means nothing. Then B to the power n. It is also very simple. I hope it is not a very complex architecture, whatever I have taught till so far. Only thing is that if it is a plus symbol is coming, that means two paths you have to travel. If it is a node, it is a node. Then these two paths. This is a plus means this is A path and B path. It is a plus B path. If you want to check A into B path, A into B means this is a node. This is A. This is another node. This is another node. It should be A and B. These two principles you have to remember. Plus means OR path and consecutively means followed by path. By that you can check. And some more examples I have given here. You should work out here. So what we have learned in this finite state machine phase, that if a grammar is given, definitely the grammar should contain production rules. I can generalize the grammar either in form of this expression format or using this tree format, syntax tree format, and can obtain a language. This is a language. For the language, I can take different strings, what it is accepting. These are the strings different or the sentences. So for that sentence, it is following the grammar that is being taken initially, because from grammar to production rule to language to sentences to grammar again. And for the language, our task is to design a finite state machine for a language. And the language should be checked by the grammar. That means should be accepted by the grammar. Because the grammar, from the grammar I have designed the L. Definitely the L should accept the finite state machine. That means the finite state machine will be accepted by the grammar. Again, I'm repeating the sentence. From grammar we have designed language. If L corresponding to L, if I can design the finite state machine, that means definitely the grammar is also accepting the finite state machine. Okay, that's why whatever the examples I have shown here, that is based on L. So that means if I can design an corresponding finite state machine for L, that means this finite state machine is also accepted by the grammar. That is the main point that we want to check out here. Okay. So these are the preliminary parts that I want to introduce, and let me check what more are there. Okay, this is one example I had given, that what are the different phases of compiler design. That this part I will be coming in the next lecture. I hope. Let me summarize what I have covered. This is the foundation lectures that I have started. We started with the different phases of code processing: preprocessor, compiler, assembler, linker. Then we start understanding the different phases of compilers. First phase is related to the finding errors. Second phase is connected with the optimization. Then we have understood what is called token, identifiers. We have understood what is called syntax tree. Then we have understood how the infix, prefix, and postfix can be evaluated easily. Then we have come across symbol tables. Then we tried to introduce what is called grammar and language, and what is the relation between grammar to language to finite state machine. Then we have seen some examples on the languages, and for today this is only first part. The second part will be covering this is the foundation part. Yet I have not started the lexical analyzer part, so we'll be covering in the next class.